great to see you again. So, for those who don't know me, I'm Wojciech Mazur. I'm working in the Scala free compiler team at Virtuous Lab. I'm also the main maintainer of Scala Native, so the custom runtime for the Scala. And actually, I'm part of a Scala core team, where we actually sometimes need to decide on some changes to the language. And one of such changes recently was the change of the required JDK version. This one would bump up in the upcoming JDK, Scala 3.8. So roughly by the 8th of this year. That's not the first time that it occurs. However, we actually it was required by us because so that we can actually fix the problems that we actually have with implementation of lazy vowels that are powered by SunMISC unsafe, which unfortunately recently is very verbose about its deprecation, and we don't want you to see a lot of warnings at runtime when running your logic. So the last bump like that happened in Scala 2.12 with the JDK 8, so roughly 10 years ago. In the meantime, there was a lot of improvements to the JVM. A very single release of Scala, of the JVM, comes up with at least a dozen of Java enhancement proposals. So a well-structured improvement to the Java JVM or its ecosystem. And even if you would stick only to this LTS version of JVM, they still like build up. There's a lot of innovation going in here that also we, as a part of compiler team, can use to make our language better or make it more performant, for example. But what actually improvements are introduced in it? So every single JEP has an assigned area in which it tries to improve. And from our perspective, there are two that are the most important. The core, which is basically the internals of the JVM or some parts of the bytecode specification or the JVM specification on which we can build upon Scala features. And the second area is the hotspot. That's the one thing that actually the JVM runtime that is powering all of the Scala applications. And this one actually is improving the mostly your life of your applications, because with a very single improvement to garbage collections, to better just-in-time compilation, or better implementation of some parts, you actually benefit directly even without changing your code base by just upgrading the Scala JVM version that you use. However, people typically don't really want to track a single JEP. And also, the OpenJDK collective wants to have some long-term goals. Similarly, as today Martin has told us about his long-term goals for Scala, similarly, OpenJDK has its own goals in which they want to JVM evolve. For example, the project Amber, under which they have defined multiple JEPs that were introducing new concepts to the Java language. For example, records, or the sealed classes that we all love and use in the Scala. And at the same time, they also are introducing, in this case, some improvements that we, as a Scala, can also use, because maybe some additional attribute would make the interop between Java and Scala easier, for example, in case of sealed classes and checking the pattern matching from the Scala for the JVM inputs. However, we are going to talk more about Scala Native today. And Scala Native has its own runtime, which is independent from JVM, so it cannot directly benefit from all of these improvements. However, for us, especially for me, as I work in Scala Native, JDK is only an interface for a standard library that I need to implement and that you can use, and which you can actually reuse. So based on that, we can re-implement some stuff that you can find in Java, for example, Loom and its APIs. However, different projects might be completely irrelevant from our perspective. For example, garbage collectors, which are very entangled with the internals of each on the runtimes, cannot be directly translated. There is so much going invariants inside that porting from implementation, for example, from JVM to Scala Native makes little to very no sense. However, they can give us some hints how we can improve. So we're not going to talk about it, GCs. Some other projects might be fixing problems that are existing only in the JVM. For example, the startup time, which is improved by the Leiden project by providing, for example, ahead-of-time compilation. This one, again, is not the case for Scala Native. We have always been compiling to the ahead of time, so no intersection points as well. Similarly for Amber, because that's only proven to Java. So we are left with 4 projects, and today I would try to tell something how actually Scala can benefit from either the API they provide, or maybe by some concepts that they introduce. So let's start with the elephant in the Loom. So the core of the Loom was the JEP 425, which was introducing the virtual threads in their original implementation. And it was then building other features on top of that, so the structured concurrency or scope values. And later it was, for example, introducing some later improvements, for example, making the synchronization of virtual threads more sane when it comes to the pinning, so making the interaction with the existing code bases much more easier and performant. However, we can potentially, as I said earlier, reuse existing Java APIs. So, for example, thread builders of virtual, but we need to somehow implement the virtual threads. But how to actually do it? We actually need 2 things. The first one are the fibers of delimited continuations. So what delimited continuation is some way of transforming your code, or you're providing some runtime functions that would allow you to create some task, invoke this function without exposing any coloring for your signatures. So there is no distinguishment between calling normal function and a function that can suspend. And when you do execute your code, you create, you allocate some stuff on the stack. These are so-called activation frames, which contain all the state that a program needs to resume from this function call. It, of course, could be nested, on and on. And at some point, we can get to the point where we, in our code, tell that I want to suspend this execution. And what it means, I want to take all of this data that exists, I want to make a snapshot of it, and continue executing my code from some different point. In our case, for example, the next instruction after invoking this suspendable function. So here we can do something else on the stack, and at some point, we can actually resume the previous computation, resume the state saved on the heap, for example, and continue executing our code like in a case where there was no suspension at all. As you can guess, the thing is not so trivial. It touches some very low machinery of the runtimes, especially touches registers, because, for example, this needs to be preserved. Also, we need to somehow jump out of the function and then point it back. So that's not trivial. However, actually, the Scala Native is supporting that for almost a year now. In Scala Native 0.5, there was introduced a continuations API, which is now powering the Gears project. So the project that provides us with some structured concurrency that on JVM builds on top of Loom, in case of Scala Native builds on this API, and defines some API in which we can create a boundary that marks the point of our program in which we can suspend, and some functions that can possibly return some value. So that, for example, we can create a generators even with this API. So when having that, we can actually wrap some ordinary task. So for example, any ordinary runnable that is defined anywhere in your application, and used our continuations API so that we wrap the original function inside the boundary, and then run it. And this function can or might at some point suspend. If it suspends, we can, on next invocation, use the stored handle to the function that continues executing and continue our work. So this would provide us with ability to create context switching. Context switching that is not done by kernel or operating system, but by us, the users, and where we are in control on when program needs to suspend on our wish. The second thing that we actually need is some way of running these suspended continuations in a performant way. So for that, let's take a look first at system threads. These are run by the mentioned previously scheduler running on the kernel level. And the system threads that we use, so ordinary Java thread that is powered by them, are quite heavyweight. So the context switching is quite expensive. With virtual threads, we can potentially create thousands of these small, short-lived, lightweight threads that basically wraps our task to make it suspendable. So what we need in between to run them in some decent and performant way, we need to introduce our own scheduler. So we define some pool of threads, let's call them a carrier threads, that their only responsibility would be to pick some of virtual thread that is available and mount its task on itself and continue executing that. In JVM, this is backed by a fortune pool in most cases, but can use some additional pools for some recurring events that can happen. So now we can create a special variant of virtual thread that is called a virtual thread. And this one would override the start method. Instead of running things directly, as that would be happened with normal ones, it would instead delegate execution to the scheduler, which would then mount it on one of the available virtual threads at some later point. So we can now start the virtual thread, but we don't yet have ability to suspend. And I mean, by that, I mean that we have no direct API to suspend execution. Maybe not, maybe that's a bit exaggeration, because there is a Java-lang thread yield method, which actually we can re-implement, change its implementation, so that if it detects that we are running virtual thread, we would suspend execution using dedicated API, and then, for example, submit it for later execution later at some given point. Otherwise, we can just give the hint to the kernel that, hey, I want to suspend, but it can ignore it. Similarly, we can completely suspend some given thread from executing. For that, we can use the similar approach. In that case, however, we would not schedule it directly. We would rather wait until the given thread is unparked. This API is actually implemented by the Java utility concurrent lags support, which then is used by most of the classes used by Java utility concurrent. So they are actually managing the threads and suspending their execution. In that case, actually, we can also use, in terms of parked timing, we can actually use our secondary delayed scheduler and tell that I want to suspend execution, but if I don't unpark the thread by myself, the runtime can do it on its own after some delay. However, there are other caveats that we need to remember about. For example, blocking operations. When we enter some blocking code, potentially, for example, a blocking function defined by the system, we don't have control about the suspension. So for that, the JVM temporarily can increase parallelism of our runtime, of our scheduler, so that it can create additional carrier thread to compensate for thread that is being blocked. And later, when the blocking operation finishes, it decreases parallelism so that the scheduler can reach the equilibrium, so it can reach a state in which we can reach the best performance by limiting the amount of system threads that are used. Similarly, some integrations might be actually done in case of non-blocking I/O, so that we can actually make some better decisions about, for example, when the resource is available, and we don't need, for example, to poll directly for information from the system about that. And can it actually work? Yeah, there is a part in the Scala Native that actually implements the dining Scala layers just after the launch. So I've re-implemented the dining philosophers problem and run it using Scala Native. So we would start some amount of virtual threads, and this would be suspended by other thread sleep or when acquiring the lock to the semaphore, because the semaphore underneath calls the parking methods. And if you would take a look at the actual outputs and track a single virtual thread, we would see that it is sometimes executing on worker number 1, sometimes on worker number 5. So the work is actually distributed, and these are actual virtual threads that are implemented. The work here is not yet done by us. There is still a lot of problems that need to be solved before it is stabilized. But in the near future, Scala Native would have actually the Loom implemented in itself. Okay, let's get to the other projects. Liliput, the small one, but with very big impact. So the Liliput actually does not provide us with any API, but instead focuses on runtime improvement, from which we can really learn when it comes to our implementation. It introduces a better object headers implementation, in which they reduce the amount of space occupied from 12 or 16 bytes to only 8. However, in long-term ago, they want to reduce it even further to only 4 bytes. And it is actually important from the perspective of the performance, because if your application has, on average, objects that are small in the size, you can actually see a big, very good big performance boost just from the fact that your application would not consume so much memory. In that case, with their ultimate goal of reducing from initially 16 to 4 bytes, there's almost a quarter of data that can be saved. So what object headers and the object layer looks at the runtime level? So here, a very single object that is defined contains its fields, but at the very beginning, it contains a header. And header on the JVM consists of 2 fields. The mark work, which consists of some additional data. Actually, it's a tagged pointer that can either be a pointer with some additional metadata stored in some lowest significant bits, or some bit set with some additional information that is, for example, used by the garbage collection or the implementation to store the hash code. The second field is populated by the pointer to the actual class instance. So we can have an access to runtime type informations, which, for example, might contain information about what class are we executing. So we can actually check if it is the correct instance of. And similarly, we can, for example, get access to virtual methods tables. So how they improve actually right now in the JDK 24, is the experimental support for new layout, which consists only of a single word built from squashing the 2, which contains both improvements to the encoding of class pointers, which now take only 22 bits, and getting rid of some completely unused bits that existed before. Also, the nice improvement in here is the fact that the data is no longer overwritten. Previously, we didn't really know if it is a bit set or a pointer until we have actually checked the tag. Now it is always preserved, so data can never be erased directly. And how does it look in Scala Native? It's actually quite similar. Actually, we have regressed a bit. In the Scala Native 0.5, we went to support the object monitors and the synchronized blocks. We needed to introduce the lock word, which basically does the same as the mark word of the JVM. And it also used the bit set and the tagged pointer to store a reference to the monitor, to the potentially heavyweight monitor, keeping the actual logic of synchronization. So in that case, we can mostly adapt more of these improvements coming from their achievement, their research, and improve by both getting rid of this mark, squashing everything together, and optimizing how we actually perform the mapping to the from between the object and the object monitor. The last one, I think, that we would be able to talk today is the Valhalla. The Valhalla, so probably the longest running project. I think the very first mention of it comes from around 10 years ago, and it's still not there. But actually there was a lot of stuff already implemented and merged, or that's going to be hopefully delivered soon, so that they can provide us with value classes in the JVM itself, and also improve how generics are working. In fact, there's also a lot of drafts for future enhancements, but these are mostly blocked by the initial problems. And in the past releases, there was also like a lot of actual dependencies of Valhalla already merged. So there is some progress, but we still need to wait. And the problem that Valhalla actually fixes is the memory layout and cache locality. So we can define in Java a record, and similarly as a Scala the case class. And for example, if we would have an array of such an entities, a very single one of them would actually be a pointer to some place on the heap. But it can be basically everywhere, anywhere. So the cache locality is not very good, and there is a lot of intermediate steps that is required to actually read the information by traversing all these pointers along the way. With Valhalla and value classes, actually the whole layout of all value classes can be inlined in place. So in case of this array, we actually no longer have a reference living somewhere on the heap, but rather have it stored directly where the array lives. So we don't even need to make any additional lookups. We can basically just have one computation to compute the address to the given field and get access directly. So it's both allows us to preserve memory space, because value classes do not contain object header. They have no identity. And they also improve the overall performance. So no identity. That means, as I said, no object header. So that means that stuff like equals and hash code needs to be implemented a bit differently. So similarly as case classes, only based on the actual fields, which might be kind of surprising in some cases. But also there is no heap allocation by default. If the value class is embedded in an array or some different structure, for example, is a field of a class, its fields are already embedded within. And the only cases when actually the boxing and heap allocation and introducing identity, so object header is required, is when we would pass it to some erased context, or where we need to access the runtime type informations. So for example, for virtual methods dispatch, if we cannot deduce them at compile time. So the second case, like the one with the generics, actually can be improved. So the Valhalla also wants to improve how to allow for dealing a bit better with generics. You might think that actually it was doable in Scala already. However, there are some caveats. We can, of course, use the primitive types as a type argument for our generics. However, at runtime, these can be actually boxed. So both the input and the output needs to be boxed and unboxed after receiving the result. That happens because we still need to validate the contract that the JVM introduces. So we need to create additional bridge methods that are erased objects. Valhalla actually wants to improve on that. They want to introduce some kind of specialization of the generics that we had a bit in the Scala 2.12. However, I don't think it is already fully defined at this point. Can Scala Native can learn from that? A bit, but not really. I mean that it's very hard with current setup to track all the primitive types and to deal with existing assumption within the compiler. However, there are some proposals how we can improve. I know that there's already some research going on inside the EPFL to implement so-called inline classes, which would behave a bit similar to the value classes. And Scala Native can, at that point, use this implementation. However, I think it's still a long way to go before it would be reached, especially because Valhalla is still highly experimental. Some other use case, possible implementation might come from trying to implement native structs, because Scala Native has also some way of having the interop with the C, and for that we would like to have be able to define some interfaces, or the C structs, and make them work without any additional boxing. I was trying once to deliver such a proof of concept. However, it was actually very problematic to make it actually work, mostly because like I said previously, there's a lot of assumptions in the compiler code transformations and syntax desugaring that we are not in control of at the point of compiler plugin. So we can't really benefit from it yet. So probably we would need to wait until Valhalla is shipped inside the JVM and later in the Scala at some later version. Okay, we have just a couple of minutes more. So just a quick mention about the Panama. So this one actually is defining two jobs, one for foreign function, the other one from vectors API. Both are highly experimental. One is in the preview, the other one still in the incubator. And in case of function API, we are able to define some bindings at the runtime, actually, which later can be optimized by just-in-time compilers, so there is no overhead. We can't really use it directly, but actually it might be useful for the Scala Native so that it has some way of defining bindings dynamically. Currently, it is very static. We need to define the external object with some definitions, and these functions need to be always present in some ways on the system so that the actual program compiles. But we don't really have any API for stuff that might be available sometimes. So we might consider adding something like that. And the other thing, the vector API, which allows to vectorize the operation that you perform. Currently, it's mostly up to the optimizer, the LLVM optimizer, to vectorize some operations, but there is no direct way to control it right now. So if there already would be introduced some API, why not build upon it instead of reintroducing our own implementation? That might not be perfect. Especially because in the case of these two, if you would implement them, we can, for example, take advantage of quick prototyping on the JVM, which has a quick feedback loop, and then perform a bit slower compilation using Scala Native and have the same results. And in case of vector API, you can basically map it mostly one-to-one to some low-level operations at the LLVM level, which would be then very performant. Okay, I think that's all from me. As you can see, we start trying to evolve, similar as Scala is evolving. We're trying to keep up, so we are not left behind. And at some point, when new features become into Scala, we can actually be on par with the remaining runtimes. And if you have any more questions, I will be waiting in the Scala Space booth if you want any additional questions.